Cool. Is there anything I can do for you all? Any sort of questions or anything? We got a web work, right? We got a web work floating around. Yes, ma'am. You're just stretching. That makes life easy for me. I'll take that. Hello. Does anybody have anything they want to talk about? We're going to do a little quiz on Wednesday, I think. Is that correct? Yeah? Yeah. It's going to be over that web work, that recent web work. So basically, quiz Wednesday. Let's just make sure we all know what's up. It's easy. It's just going to be the power rule for differentiation, and you can practice that on the web work. I'm definitely going to also ask you to find the equation of a tangent line. That's the very last problem on the web work, I think, but we're going to practice a bunch today. And you just let me know if you want more practice problems like that. And let's just say maybe sine and cosine graphs, because there's a few folks who need to show me they can make those real pretty. And so you never know. They might be on there. I'm not sure about this green. Let's do something else. All righty. Let's get a couple more differentiation rules up. Oh, let's put our list over here of things that we know. So differentiation rules. This week things are going to get much deeper. So like today's kind of the last day before we really step off into the deep water. Still chill. We're still talking about some simpler things. But on Wednesday, we're going to talk about a rule called the chain rule. And that's when things get interesting or tricky. And for those of you who, like, I can't seem to stump with problems, welcome to the chain rule, because I'll be able to come up with all sorts of fun stuff for you to miserate over. So differentiation rule. First one is we've got the power rule. And I would have these guys maybe just write an informal list that you have next to you. So until you get used to these things, and that is the derivative of a variable raised to a power is you bring that power out front, decrement the power by 1. We practiced a lot with that. So I've got a good feeling about you rocking on that. We also talked about this rule that if the roles are reversed, so in this one, the variable is the base, the exponent is constant. Here, the exponent is the variable. The base is constant. This has a natural log of a that comes out in front, and then you just recopy the whole thing. Easy, easy, easy. Just pop that in front. You just took the derivative. There's a special case of that, which is the greatest rule in all of math. It's just that the derivative of e to the x is e to the x. That's going to happen. You're going to see that a billion times this semester and in your life as you go forward in science and business and economics, whatever the heck you're doing. There's a new one that I want to put up that we didn't talk about, but if I have the derivative of the natural log, and here I'm going to write this in a couple ways. This is absolute value of x. That is just 1 over x. You might see this without that absolute value. So this is also the same as derivative of just natural log of x. But look how pretty that is. It's just 1 over x. And then we had some combination rules. I'm going to put those here because I got 2 more rules I want to put up there. So combining derivatives, we have that if I have the derivative of, I don't know if these are, I'm going to give you the fancy word for it. These are linearity properties. I'll explain in just a minute what I mean by that. But if I have a constant times some function and I want to take the derivative, I just pull the constant out in front and then do my derivative. So forget about constants, just move them out in front, carry them along. And if I have a sum or a difference of two functions, I just do each derivative in turn. And again, I'm going to play with notation here. Just write the derivative in a separate way. So we got all that stuff. We spent some time with this, but not this. And I'm going to put two more rules up here. The derivative of sine of x is cosine of x. And the derivative of cosine of x is negative sine of x. Let's actually talk about that. I'm not going to prove this. This is like proving this is like not something you want to see anyway. You don't want to see it, but we can understand it. Like, why is that so? And this is the thing that people commonly screw up, that minus sign. So the derivative of sine is positive cosine. The derivative of cosine is minus sine. Let's take a look at that derivative of sine and see if we can understand that graphically. So first off, I'm just going to sketch out sine of x. Let's make that graph, and we all know how to do that quite beautifully. So the legend goes, and we got 1, and we got -1, make ye old box, and we're doing sine, so choo 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 choo. Kind of, right? Kind of shitty, not great. There we go, a little better. So the derivative is how the tangent lines change, right? We're thinking about the slopes of the tangent lines. Oh, I got a purple here. This will work. Great. So this immediate slope right here, it's hard to tell from my picture, but that slope right there is 1. I'm going to write m equals 1. That initial slope is a perfectly diagonal line. If you look at a sine graph, that's well done. This one's crappy. And the scale's kind of weird because this is 1.7 and this is 1. So the scales are off here, but the slope at the start is 1. What's the slope right here? 0. M equals 0. What do you think the slope is right here? -1. And then we go 0 again. And then what do you think the slope is right there? 1, because it started over again. It's literally the same picture. So here, m equals 1. So when I come down here and I'm sketching the graph of the derivative, so this is going to be derivative of sine of x. Let's pretend I don't know its cosine. But I'm still making my picture. I see that the slope is 1 right at the beginning. So I'm going to put a dot right here because the slope is 1. And then at pi over 2, the slope becomes, well, let me get my nice units. At pi over 2, the slope becomes 0. It's -1 at pi. And you see where the cosine might be coming from here? We're getting that rhythm of that up, down kind of stuff. This is thrice pi over 2, where my slope is 0. And then finally, I end back at 1. And if I were to do this all very carefully, I would get this graph right here. And that wasn't very careful at the end there at all. But that turns out to be the cosine graph, which is not hard to believe. So now let's take a look at the derivative of the cosine graph, because it says it's sine. So let's see if we can see that. I just want you to have a rough intuitive feel for this. So here's twice pi, here's pi, pi halves, thrice pi over 2, 1 and -1, make me box, make me dots. So I'm doing cosine now. Every time it crosses the x-axis, it's at a slope of 1 or -1. What's the slope right here? 0. M equals 0. What's the slope here? 0, right? And then I'm not going to make Sam say that again because we know he's going to say 0 right there. You're going to say 1. Sam, what's the slope right here? There we go. Ah, gotcha. And then here it's 1. So now let's sketch the graph of the derivative of this thing. Notice that it's 0, but it immediately has a negative slope. So when I come down underneath and I start to sketch this derivative, 1 and minus 1, pi halves, 3 pi over 2. I get my little, I'm just setting up the box even though I didn't know theoretically it's a trig function. So we start off with a slope of 0, got a slope of 0 right at pi, got a slope of 0 right at the end. And then it goes to -1 right here. And then it goes to +1 right here. And if you sketch this baby out, it's exactly a sine curve turned upside down. So if this is sine of x, this is minus sine of x. You just flip it over the x-axis. So I just wanted you to see that. That's the only way we're going to prove it, but it's believable that this is the case, and that's why we've got that negative twist on that one. Any questions over any of that? All right, so you got a little derivative table you're making. You're going to have that by your side so you can do all sorts of stuff as we go through this. Let's start with let's do a quick bit of review. So find the equation, we're going to do tangent line, of the tangent line to y equals x squared minus x, that's nice and chill, at x equals 2. So step 1, let's go through this together because it's been a while. We haven't done a lot of these. But step 1 is going to be find the derivative. In fact, that's step 1 for the rest of the semester. If you get an expression and you haven't taken a derivative of it, you probably haven't done the problem yet. Remember, there's a secret 1 right here. Yeah, I don't have any super tricky stuff for you yet.
Okay. I'm just taking slow notes. So.
Good. Awesome. Look at that. You even got paper and shit. Look at that. Damn. Looking good. Looking good. Yep. Nice derivatives all around. Doing here. How'd you get? Oh, you're doing the line. You just kicked ass so fast that okay. I was like, wow, that's an interesting derivative. Does it make it? Yeah, good. That's right. That's right. Yeah, beautiful. Beautiful work. And then bring that minus out in front so you don't have to think about him. Yeah. Oh no, this guy right here. See how you were carrying him here? Because you don't have to think about him. It'll just be minus the derivative of x to the first. Okay. Does that make sense? Yeah. Cool. Great job on the other one. And how we doing here, my friend? Yes. Good. Excellent. That's the step. Yep. Doing here, looking. Yeah. Yep. Beautiful. I didn't check on yours, Sophia, but I got a feeling you got it. We'll find out. You'll find out secretly. Did I look at it? Did I? I can't even remember what happened. Okay, so the derivative, y prime, or look, I'm just a little notation, dy dx. Oh, that's right. Yeah, now it's all coming back to me. Forgive my old mind. Is the derivative of the right-hand side, so the 2 comes out in front, x to the first, and then minus, I just copy that down, the 1 comes out in front, times x to the 0. That's just 1. In fact, a great little rule of thumb is that the derivative of just some multiple times x is just that multiple. That's just a good fast rule to have ready. If you just have some 3x, the derivative is 3. Minus x, the derivative is minus 1. So this is 2x minus 1. Well done. Step 2, plug the value of x in. We still need to get our point. There's some data we need to get here. So first off, let's get the slope, m, at point of interest. So that slope here is going to be the derivative. I'm going to introduce a little bit of notation here as well. And apologies over there on the left, friend. I'm going to start writing low. It's going to get, we'll have to do something. Wow. But she didn't imagine I was so powerful. So m equals the y prime. Now check out this notation, a straight line. This means evaluated at x equals 2. That's a notation to help myself remember what has to happen. So that is the expression 2x minus 1 with x replaced by 2. And that's just 3. 2 times 2 minus 1. Step 3 is you may or may not know the x and y coordinate of your point. If you don't, you have to find it. So step 3 is if we need the y coordinate for the point of tangency, plug it into the original function. Get it. And so this is all back to the original function, no derivatives. And so here, when x equals 2, y equals 2 squared minus 2, that's just 2 again. So it worked out nice. Let me stop for a minute and make sure that I'm not just steamrolling. Everything seem okay? Some of you already got the problem done like ages ago. So you're probably just hoping I get through this and get done with it. All right, so I got my point. I'm going to use a little notation here. So x sub 0, that's my point. And then y sub 0, that's the y coordinate of my point. And the reason I do that is because I want to use point slope form for the line. And I actually didn't see anyone do this on that last quiz. That's why I want to talk about it again for equation of line. And that equation looks like this. Y equals the slope times x minus the x coordinate you know, plus the y coordinate you know. So here m equals slope, x naught, y naught equals point on line. Please know this and use this. You can do the y equals mx plus b, but this is just more straightforward and will actually help you when we start applying this stuff, having this form here. So for us, it's going to be y equals the slope of 3 times x minus 2 plus 2. And we're done. We're done. We could simplify this if we wanted. It's 3x minus 6 plus 2 is 3x minus 4. If you want to go that route, beautiful. Go for it. But this is what I need you to be able to get to. All right. Let me talk about what we just did. We took this graph right here, this parabola, which looks like this. And we found the equation, this is 1. We found the equation of the tangent line at 2. So there's 2, and then that was 4. Or, well, I guess the output's also 2 over here. When x is 2, y is 2. So this is the point 2, 2, and we found this guy. We found that tangent line. Why would you even want a tangent line? Because you can now use this as the approximation of that function near 2. So the reason you do tangent lines is because sometimes you've got some god-awful equation, x over x. You got some horrible thing you don't want to work with. So you take the derivative near a place you're interested in, get the equation of the tangent line, and then instead of worrying about some nuttiness like this, you're like, oh, it's actually just a line right by there. And you use that simple equation just near your point. We'll get into that a little bit more, but I wanted to put it in your brain as a seed. Are we good on this? Can we do this? All right, now we're going to do it like crazy. So let's start practicing, but let's introduce a few good rules. So new rules, in addition to these guys here. We'll put them up over there. We don't always have these nice functions that are just like, oh, it's just x squared. Oh, it's just sine of x. Things are a lot more complicated than that. So we have a couple of rules for expanding the things we can take the derivative of. And this is the first big one. If I want to take the derivative of the product of two functions, so f of x times, that's a times right there, times g of x. The rhythm is derivative of the first times the second piece left alone. So note, I'm just doing that derivative. I'm copying that along, plus the first one left alone times the derivative of the second piece. I'm not going to prove it. You can read the proof in the book if you want. Nobody's ever been upset that they didn't see the proof. Everybody seems okay with that. You believe me. You've had calc, you've seen this before, so you know I'm not lying to you. So let's practice this. Let's do a quick example. Derivative of x squared times e to the x. Notice how I said it. I read the problem in my head, and I want to encourage you to do this. Don't just look at the page. Say the thing in your head, because I said the word times in there. And I bet you do too when you read that. You might read it as x squared e to the x, but think about the operations. As soon as I say times in there, this tells me product rule. I got to use the product rule. And at first, you might want to write this out. So we're going to be careful. Once you're good at this, go crazy. Derivative of x squared times the e to the x left alone, plus the x squared left alone, times the derivative of e to the x. The best derivative in the world. Derivative of x squared is 2x to the first. We just did that one in the last problem. E to the x plus x squared derivative of e to the x. If I don't remember, I look at my little table that I've made and I see it's e to the x. Done. Done. I could. Now, some of you will want to, and I like that you'll want to, simplify this a little bit, or not simplify it, kind of factor it to make it look like that, and that's a good move. Do you see how I did that? I pulled the e to the x out. If I wanted to do a little bit more, let's just talk about it. I could pull an x times 2 plus x e to the x out. The reason I would want to do this is because now I can look at this and answer the question, when is that equal to 0? It's equal to 0 when x is 0, or x is what? What makes that 0? -2. And that's not obvious from here. So at some point, you'll want to push things beyond this first step, but for now, just get that first step working properly. Any questions on that? Are we good? this product rule can actually extend to any number of things multiplied together. So if I have, it extends. If, for example, I have the derivative of three things put together, f of x, g of x, h of x times f of x times g of x times h of x. Same game, everybody gets a turn. So let's just abuse notation a little bit. It's f prime times g times h plus f times g prime times h plus f times g times h prime. Everyone gets a turn, gets one turn at differentiation. And a very common mistake is to just say, oh, it's f prime times g prime times h prime. You got to remember these special weird rules, and I'll help you remember them as we go through. So let's try one. Let's try some stuff that we're just starting to get familiar with. What is the derivative of x times 3 to the x times the natural log of x? Everybody gets one derivative. So you'll have three things added together as a sanity check. I won't always write everything out so detailed, but today's day one of this. Everybody gets a turn. Got three things. Just for those who are pretty sure they got it. Natural log of 3 comes out on that guy. This guy. If you feel like simplifying it, give it a shot just to see what happens. Let's do that. And while we're waiting for everybody to get their work done, get caught up with us, we can do a little vanity algebra. I think that looks okay. You think that looks okay, Sophia? That doesn't really inspire confidence in my answer for me. How's that look? Look okay? Anybody agree with me? Anyone have any questions or troubles with getting that answer? You don't need to do that factoring part. This one's really weird. as long as you can get to this, and the thing that I just wanted you to notice is these guys cancel. That's kind of nice. So that 1 over x and x cancels there. Everybody good? Kylo, you good? Yeah. Okay, cool. Jasmine, how you feeling about that? Okay, all right, I'll trust you. Cool. Let's do another one. What is the derivative of sine of x, 2 sine of x times cosine of x? See if you can simplify this. And if you know any trig identities, see if you can pull any of those out of your hat. But after the derivative, not before. If you do it before, things might get stressful. You're doing good. Okay, cool. Sleepy. Yeah. Did you have a rough weekend? Oh no. Oh no. A lot of work. Had to work a lot. Oh, it stinks. In addition to all the homework and yeah. It's good to have jobs. Good. Yeah. Good. That's a good attitude. Take that. Exactly. Exactly. I don't know if I agree with your answer. Show me what you were doing here.
So derivative of that.
So that's a constant.
Yeah.
Derivative of that's 0.
Exactly.
Okay.
Wait, and that means that's
Right.
canceled out.
Right.
But then
Okay, I like that.
That's fine.
Is the derivative of, and you did derivative sign. Okay, I'll buy that. Yes, that looks good. Yeah, yeah.
I was thinking that was 1 for a second, but
Oh, yeah. But so you can just pull it out in front. You can do what you were doing there. But in general, I would just bring him out front, carry him along like that.
That makes sense.
Yeah. One thing I just want to point out, and Sam was doing this, and it's totally like mathematically correct, and you might be doing it too. If you're seeing 2 times sine times cosine, you might be doing the derivative of 2 and then leaving these alone. But the derivative of 2 is 0, so it doesn't really get you anywhere. I would just pull that 2 out in front, like I did here, and then just carry it along and do the variable part. Not that it's wrong to do it the other way, but it's like a lot of extra writing. I think in the long run, it'll be a painful thing to do. So let's see here. So I'm going to do 2 times the derivative of sine times the cosine left alone. When you have this notation, that little d dx, this thing eats whatever's to the right of it. So the fact that I'm putting this like this in parentheses means it's only eating the sine. Here it's eating both these things, that full product, because they're grouped together. So then we got 2, leave the sine alone, times the derivative of the cosine, like so. Pen dying slowly. And then I remember this because I had calc, or I used my little table that I just learned the values for. So this is cosine, derivative of sine is cosine. Already had a cosine, plus 2 sine, and this is minus sine. Look how I'm going to put that in parentheses. Don't get suckered into thinking that turns into an addition or something. So I'm using parentheses there to keep my brain straight. So that is 2 cosine squared of x minus 2 sine squared of x. How do we feel about that? Any trig identities floating around in here? Yeah.
Cosine squared minus sine squared is cosine 2x.
Nice. Yeah, it's cosine of 2x. So this is 2 cosine of 2x. So the identity is this. Cosine of 2x is cosine squared x minus sine squared x. What is this one? Oh, Leo, that's pretty damn good. Do you know that one? Sine of 2x, exactly. That's sine of 2x up there. So we'll have a fancier way to do the derivative of that on Wednesday, but just noticing we did something kind of interesting, thinking about trig identities. So if you know the chain rule, what we just showed is that the derivative of sine of 2x is 2 cosine of 2x. And if you know the chain rule, that makes total sense. And it will to everyone else on Wednesday. Questions on this? Because I want to make it more challenging. That's not even challenging anymore. They're just like just a bunch of multiplies and derivatives. So let's amp this up a little bit with our final rule for today, the quotient rule. That's right. I'm going to prove this one just because it's kind of cool. Let's say that Q, quotient, so Q of x is f of x over g of x. I want to take the derivative. I want to know what Q prime is. So I want Q prime of x of this quotient. But I only know the product rule. So what I'm going to do is rewrite this thing. So I'm going to rewrite it so I can use the product rule. So this is f of x equals q of x times little g of x. Aha. Now I'm going to take the derivative of both sides. So take derivative. So the left side is just f prime of x. The right side, notice how I'm writing product rule here so that if someone were to read my work, they'd know what I did. If I went back and read my work, I'd remembered what happens here. So it's the q prime times the g left alone plus q left alone times g prime. Cool, just applied the product rule. Now remember what I wanted. I wanted q prime, so I'm going to actually solve this equation for q prime. So I'm going to solve for q prime of x. And that means I'm going to subtract this from both sides. So over here I'm going to get f prime of x minus q of x, g prime of x equals q prime of x times g of x. So I just subtracted this off over to here. And now I'm going to divide through by g of x, and then that q prime will be all by himself over there. So if I divide by that dude, cool. That doesn't look anything like the quotient rule you came in here remembering from calc. Got one thing I need to do. Q is f over g. So I'm going to rewrite this. Rewrite using q of x is f of x over g of x. So what we get is q prime of x equals f prime minus q. And I'm going to replace that q with f of x over g of x. And then times g prime of x all over g of x. We're so almost done. It still doesn't look like the quotient rule you remember. What's one more simplification I can do here? Yeah, I got a little fraction and a big fraction. I'm going to clear it out by multiplying by g of x on top and bottom. So equals, so multiply top and bottom by g of x. And now it's going to look like your old buddy that you're used to. So it's going to be f prime of x times g of x minus the g of x will cancel out that dude. So I just have f of x g prime of x, and then the bottom becomes g of x squared. And that's the one you were thinking it was going to be, probably. So this is the quotient rule. Let's write it out again. But that's just a fun proof. I don't get to do proofs in here too often. That one's just fun algebra. So the quotient rule. And I'm going to write it in a weird way. If I want to take the derivative of something over the bottom, so a top over a bottom, they're both variables. It is going to be the derivative of the top. Notice how I start with the derivative of the top and I leave the bottom alone, minus the top left alone times the derivative of the bottom, all over the bottom squared. You might have learned some weird Heidi low over Lodi high. Anybody heard some Heidi low over Lodi high stuff? Yeah, Addie. My first calc teacher was from Kentucky. She was like this 1,000-year-old lady from Kentucky. She was so cool. But she had some song I never understood. Heidi high, Lodi low. I don't know what the hell she was singing. Anybody know what I'm talking about? Heidi low over Lodi. What was it, Addie? There we go. Cool. Yeah, I don't know if that's much easier to remember than just having this written down and knowing how to do it. It never helped me. Let's use it. So we got the product rule, we got the quotient rule. Let's do an example. What if I have x squared plus 1 over x cubed minus 2, and I want that derivative. So d dx goes in front. Hey, your turn. Try to use this rule. Derivative of the top goes first. That's how you can remember it. The derivative of the top is the first derivative. It makes sense. It feels right. If you get done, you could go ahead and do the algebra on top. See how far you can take that. Which will be something you'll probably want to do in the future. Could do a little more. I don't know if it gets us anywhere interesting. Anybody, if you see an error, let me know, please. It's this kind of stuff that I can mess up on easily. Anybody got what I got? Yeah? Okay, cool. All right, nice. Give everybody a minute to finish up. Finally something to do in here, right?
Lots of notes.
Lots of,
I
yeah.
mean, I got bored, so I was
Yes,
doing
doing some problems.
like I was even back here, like
Yeah.
just doing stuff.
Nice.
But I'm mostly just writing what you're
Awesome.
doing and just taking notes.
That's good. Yes, sir.
Question.
Mm-hmm.
Why would you simplify the bottom?
In general, we want things factored. So when this thing is already factored kind of beautifully, I could multiply it out, but like right now, there's so much information available to me. So let's actually. I like that's a great question. Sam's question was, why wouldn't I multiply out the bottom? Well, let me multiply out the bottom, and that is something like that, right?
I got 4x to the third.
I'm just playing now. Not a super great looking answer. As long as we agree. I'm seeing nods from my second to back row comfort team. So thank you.